of this that I can post. Okay. Yeah, obviously, the last unthinkable thing. Dr. Cheney and I were talking the other day, and I told her I thought, maybe this group was somewhat bad luck for me. I don't know, that I'd had several things that had happened during the course of this class, more so than normal, and the last one being my computer frying. But I do have 3 sections, so I don't know which one I would actually have to blame. Maybe it's an interaction between the 3 or whatever. But anyhow, we're going to get this course done. We're going to get it done in a pretty decent way. We meet tonight and the next 2 weeks. Tonight we're going to do the quantitative stuff that I would have liked to have done a couple of weeks ago. Next week we'll do the qualitative sort of introduction stuff, along with a little discussion about mixed methodologies, because it is an important part of the research process. As we go along, we'll obviously entertain any and all questions about where you are with particular projects and things like that. As also, you'll find that I'm more than willing to meet with you individually via Zoom or whatever, if you have individual questions or individual concerns about things. And so, with those sorts of notions in mind, we'll move forward here a little bit. I originally had the first real, quote unquote, kind of draft of the final project due on the 17th, but I'm just going to back that off to the 21st, because we're going to meet on the 21st. And as it turns out, the 17th really is going to, the 18th I have to be out of town, and so the 17th really wouldn't make any sense. So we'll make it, by the 21st, which is the class meeting time that Thursday. So with that in mind, everything else kind of holds with the schedule. And I guess the first order of business is to see what questions, what comments you might have before we start talking about quantitative stuff. Okay. All right. Let's kind of launch into the quantitative stuff. The really beginning of sort of the quantitative approach to research was the introduction of the what was at the time called modern scientific method, back in the middle of the 19th century. Okay. Okay. In the middle of the 19th century. And, what was happening at the time in terms of historical aspects was that the world was right in the middle of industrial revolution, and things were moving along at a fairly rapid pace. There was a sense that science was moving forward, and sort of our understanding of the world was limited by our ability to demonstrate those notions that we thought might be there. And the old kind of science, the sort of empirical process that had been in place for 1,000 years or so, maybe not quite that long, was one that was dependent upon collection of large amounts of data. And once you had a sufficient amount of data, taking a look at it and figuring out what it says. And so you didn't start with a hypothesis and a prediction. You started with okay, let's go collect some data and see what we can figure out from it. And that worked pretty well up until the 19th century. And then, as I said, things began to move along pretty fast in terms of the Industrial Revolution. And some of the things that were limiting society's abilities to, develop new things and do new things and do more exciting and more innovative things was the lack of a scientific discipline that would allow you to do that, because it took too long. And so what we potentially could have done if we had known about it, we were limited as a society, or societies around the world, because we couldn't test it. We couldn't know for sure. And so that led to the emergence of what was at the time and still referred to in some middle school classrooms as the modern scientific method. And it's that notion of the experimental model, where you have an experimental group and a control group, and you do something different with the two groups, and then you measure them to see how they're different. That's kind of the sum total of what we teach as this modern scientific method, but it's got a little bit more behind it. And it's that little bit more we need to just talk very briefly about, and then we can. Strange noise here. I don't know what that is. We have a new little kitten running around the house, and even though I think I locked her out and closed the door to my den, I'm never really sure about that because she's so tiny and it's kind of hard to spot her. So if something wanders across the desk here, it's some really small little kitten. The modern scientific method really was sort of a creation of a different sort of philosophical mindset, where the previous quote unquote science had been inductive. In other words, you just collect a lot of stuff and then you make some sense out of it. The new methodology was designed to be deductive, where you would start with a hypothesis and make a prediction based on the hypothesis. And based on that prediction, you would construct an experiment or science to measure it, to look at it, to figure out, is this something that, does it happen as we thought it should happen? And as we predicted it would happen. And so the methodology really began to emerge from that logic model, that deductive logic model, but it had to be built. And there were a couple of rules, a couple of things that we knew about. And let me see if I can find okay. Let me shoot over to a little handout here. And it's kind of what, for lack of a better term, I call basic logic of deductive or quantitative methodology. But in the real world, if we wanted to demonstrate that something, there was a cause and effect relationship between things, in other words, that if I did a certain thing, something else would happen. The only ways to really know that was true involve things that are impossibilities. One of those impossibilities is that if I had an infinite amount of data, in other words, if I had all the data, if I, for example, the example I give here is that if I wanted to know whether gender was related or there were differences between IQ scores on gender, based on gender, if I was able to collect every bit of data on everybody that lived or existed in a certain population and IQ scores, then I wouldn't have to worry. I wouldn't have to wonder about that. I could simply just aggregate all the data and look at the average IQ of females versus males, and I could show cause and effect that one or the other had higher IQs. The other possibility, the other way is what we call counterfactual model. And that's where if I were, let's say if I, and maybe I've used this example before in here, I don't know, but if I had a headache and I took 2 aspirin, and an hour later the headache's gone. Well, my natural assumption is that the aspirin caused the headache to go away. So I have a cause and effect. The aspirin as the cause had the effect of doing away with the headache. But I can't ever be sure because I don't know what would have happened had I not taken the aspirin. And that's called the counterfactual dilemma, that you can never really know what would be the case if you had not been in a certain circumstance at the time that you measured it or looked at it. If you were in some different circumstance, maybe the outcome would have been different. But you can't know because it's counterfactual. It's counter to the facts in front of you. And so given that we can't have an infinitely large sample, and given that we can't know what would happen at the same time in a given space under 2 different conditions, we can never really know cause and effect, but we can estimate cause and effect. We can estimate what might happen or what might not have happened. And we can do that based on 2 very important old laws, one of which is called the central limits theorem, and that goes back to the 17th and 18th century. And essentially what it says is if you collect enough of some randomly occurring thing, you end up with a normal distribution of events. And it's not a mathematical notion, it's a logical notion, but it also happens to be true. That if you collect enough of some randomly occurring measure or data, and you look at its distribution, it will eventually become normally distributed. In fact, theoretically, philosophically and theoretically, at infinity, everything is normally distributed. In that, in the middle, it's a lot like each other, and on the ends is where you see the exceptions or the differences. And there's much, much fewer of those. The second sort of law, which dates back to the 17th century, holds that for when you do random samples from populations, those random samples will mirror the probabilities of the population. And as the size of the sample gets larger, the mirror will become more perfect. In other words, if I have a sample and it has a particular, let me go to my trusty little visualizer over here, that if I have and this is similar to a handout that's up on the web page, but if I had a population of some size, that's not working, let me get a darker pen. If I had a population of some size, and let's say I measured something in that population, and the mean was, say, 100. And let's say n here is not quite, but approaching infinity. If I went into that population, randomly sampled 50 individuals, looked at their measure, and called that group A. The mean for group A, our best prediction would be that it would be 100 also, because if it's randomly sampled, it will have the distribution of the population it comes from. And if I go back in again and say grab another group, group B, and I randomly sample group B, the mean of that will be roughly 100. Well, that's my best guess because that's the distribution that the population had. And so those two ancient laws, the law of large numbers and the central limits theorem, sets up this scenario where I can have two groups, two smaller groups, if I pull them randomly from a larger group, that are essentially similar to each other. I mean, they're essentially identical, you could, I guess, say, but we know identical doesn't happen. But they're essentially mirror images of each other in certain ways because they have, if we pick them randomly, they should have the same distribution as the population. So we can assume at the beginning that these groups are equal. So if we take one of those groups and we do something to them, whatever the treatment is, and we do something different to the other group or nothing at all, and we could just call these, if you want to, an experimental group and a control group, and we did nothing at all to control group and did something special to the experimental group, and then we measured them again. And so this up here is A1 and B1 the first time we measure them. We measure them again. So this is A2 and B2. And they're different. Say A2 is now 120, and B2 is still 100. And so there's a difference of 20 on that particular measure. Now, what the modern scientific method basically said was, and listen to all the ifs, if we had randomly drawn groups and they were equal in size and they were equal in every way that we can think of, and randomly drawn groups, and then if we use different treatments with the two groups that elicited different outcomes, then we could say that whatever we did here was the cause of this effect. And that's the modern scientific method. And there's only one real issue with that logic, outside of all the ifs and assumptions we have to make about random and all those things. The problem about that logic has to do with whether 20 is a real difference. And that's the big question. That's the big problem. Is 20 a real difference? And in order to understand the fundamental of that question, we have to look at hold on just 1 second here. Let me find this thing. Okay. Let me go to a little handout. It's called the true score theory. And this is the basic conundrum that the modern scientific method had, is that anytime you have an observed score, we know that that score, and now we're talking about quantitative scores here, we know that score has two components. One of them is the true ability or level of the characteristic we're measuring. And the second one is random error. Because we know that in all measurements, quantitative and qualitative, in all data, there is an element of random error. Because instruments are not perfect, and certainly humans are not perfect. And so there's always an element of random error. Well, an even more troubling notion is the idea that there are two pieces to this error. One of them is purely random. It's just differences in a room. If you get a room full of people together and you say you look at IQ scores or whatever, are you going to come up with a differences between the people in the room? A lot of that is just purely random error within the group because people aren't like each other. Now, they don't differ as much as we sometimes think because of that normality idea, but they are different. And part of that is just purely random error. But part of it can be what's called systematic error or effect of treatment. So part of it can be systematic error or the effect of treatment. Now, what's the difference between those two terms? Systematic error means if there's some characteristic, say gender, age, ethnicity, or whatever, that comes to bear on a particular instrument or a particular measure, then that's just systematic error. If it's the outcome of an effect, it means that whatever we did as a treatment had an effect on those individuals, and so one group ended up different from another. So when we go back to the notion of, what is a real difference? Is 20 a real difference? That's what we don't know. We don't know which part of this, is random and which part of it is either systemic or effect. And that was the basic dilemma of the modern scientific method. Was we could set up experiments, we could set up models that would allow us to look at predictions that we could make based on hypothetical or based on some hypothesis. But until we answer this question, is what is a real difference and what is just random fluctuation, we didn't have any real better science than we did before. And so that led to the development of statistical inference. Now, this is not a stats course, so I'm not even going to get into the stats piece of it, except for one little thing. Almost all statistical measures, almost all statistical techniques is based on looking at a ratio between observed difference and estimated random error. And that's pretty much the basic relationship that's examined in all statistical techniques. We have an observed difference based on just the data we collect. But we have an estimate of what the random error piece would be. And so this ratio, which can take depending on the circumstances of the experiment or the circumstances of the data, can be what are called t-tests, ANOVAs, correlations, not correlations, I guess that's a beer. Regression, etc., on and on and on. All the different statistical tests have an outcome that's based upon this ratio of the observed difference that we see and based on estimated random error. And all these different tests and the measures they create, which are like the T's and the F's and the R's, and regression as a formula, which you'll recognize hopefully, a formula for a line. All those things have as their basic logical component part some ratio that looks like this, and the only difference is the nature of the data and the setup of the experiment, how many groups there are. If there's more than 2 groups, then you have to do ANOVAs. If it's if it's all what we call continuous data, in other words, scale scores, we have to do correlations. I mean, it all depends upon the nature of the experiment and the nature of the data as to what technique we use. But in all cases, it's based on some ratio that has as its top something that's based on observed differences, and on the bottom, something that's an estimate of random error. And so once that technique began to bear fruit, and we began to see how this could actually work, because each one of these different statistical pieces generates a distribution, and at infinity, all those distributions are normal. And even short of infinity, all those distributions are predictable. So we can know how much area lies under a particular part of a distribution. And that is, in a nutshell, what statistical testing statistical inference is all about is those two concepts. The idea that there's always going to be this ratio between what we observed and what we estimated would be random. And then those, whatever the statistic is always going to have a distribution. Might not look like a normal distribution because we're not at infinity, but it will be a predictable distribution that we can talk about the likelihood of being in particular areas. Now, essentially, stuff that's in the middle of the distribution like this, we consider to be mostly random. Outcomes that are out on the ends, one way or the other, we consider to be what we call significant, to be significant outcomes. Let me stop. How many of you are totally tuned out right now? How many of you have dropped off? No. Well, there's a reason why most people think the absolutely worst class that they have ever taken is a stats class, unless you happen to be somewhat mathematically interested in things. But even that is wrong because stats is not math. It's logic. And just like the modern scientific method is built upon a logic set, statistical inference is built on a logic set. Now, there's some skill involved in knowing which particular statistic goes with which particular scenario of an experiment. But that you can pick up, in an hour. But because of because stats kind of looks like math, and we have a lot of folks in society that are kind of math phobic for whatever reason, probably because they had crappy math teachers when they were young. But it's, it is a sort of a common misperception that math is this crazy, or stats is this crazy thing that really I'm not designed to understand. That's not ever really been the case. But it is if you think of it as math. But if you accept the notion that it's all logic, and we just use some mathematical manipulation to kind of move it along, then you are much better off in understanding the notion of statistical inference. So what is significance? Let's see, I think I got that up here somewhere. All right, give me just a second. What is significance? It's generally defined as having a less than 5% chance of the observed outcome being due to random error. In other words, if you think about that little distribution I just drew, all that big section in the middle we assume to be random error. And the stuff out on the ends we assume to be exceptional cases, or in statistical language, we assume to be statistically significant outcomes. And so when you hear the term significant, statistically significant, it means there's less than a 5% chance of the observed outcome being due to random error. And if you're in that less than 5% chance, then it's significant. Because those will be the two tails, or 5% on one end of the distribution, or 2.5% on the other two ends. You know, I was once asked by a school division that I was working for, doing some work for. They had a meeting, and yeah, just add one thing here. They had a meeting in which they were going to talk about a new selection process for their gifted and talented program. And the way the process is going to work was that up front, they would use this instrument, and I even forget the name of the instrument. It was one that was fairly popular back, and this is like, 30 years ago. But it was a fairly popular instrument at the time that was used to measure giftedness. And it's kind of like a super IQ test is all it was. But they were going to give kids that had been recommended by their teachers to be in the program, they were going to give them this test, and that was going to be the first step in the selection process. And the notion was, okay, what score on the test should we use to let a kid into the further, sort of evaluation of whether they should be in the program or not? In other words, there are 3 or 4 other steps, but the first step was going to be this test. And I said, okay, so we're just going to, based on this one test, we're going to decide whether this kid needs to be evaluated further. And so you're asking me what score should we use on this test in order to, kind of control the gate there so that only the kids that we thought were worthy of the time and effort could be evaluated a little further. And so, I used a little whiteboard, a little, sketch pad thing I had with me. And I said, okay, I'm going to draw this little thing here. And somebody said, oh, bell curve. I said, yeah, it's normal distribution. And I'm going to say that if you want to know what is a significant outcome for one child, to say, okay, they are significantly stronger than the group, then I'm going to say that 95% of the students will be over here, and 5% will be over here, and that's the level of what we call significance. And this is at the 95th percentile. So any kid that scores over the 95th percentile, at or over the 95th percentile, we can evaluate them further, to see if you're saying you want to do that. You can evaluate them further to see if they want to be if they should be in the gifted and talented program. And so there was some kind of rustling in the room and some whispered conversations back and forth and things like that. And so eventually the curriculum supervisor or the instructional supervisor that was going to, lead this new version of the gifted and talented program, she said, so you're telling me that anybody below the 95th percentile on this instrument, we shouldn't look at them because there's no chance they're being gifted? And I said, no, that's not what I'm telling you. What I'm telling you is that based on this one instrument, if you want to know what is a significant outcome, such that you could assess those people that showed a significantly higher score than other students on this test, it would be at the 95th percentile. And so they thanked me for my attendance at the meeting and sent me off to get lunch and said they wouldn't need me that afternoon. The program kind of didn't get off the ground. They kind of laid around or whatever. And about 6 months later, I get a call back and said, okay, what should we do? Because we know that if we just do it the 95th percentile, we're only going to have a handful of kids that we can further evaluate. So what are we going to do? I said, well, you're going to use multiple measures. And so you're not going to place a kid, you're not going to say a kid's out of the program based on, one measure, one score on one measure. You're going to go ahead and assess kids on at least a couple of 3 dimensions. And then based on those assessments, you can make a decision as to who, perhaps should go on. And then, then I spent some time helping them figure out what that assessment process would look like. And they ended up with a fairly robust gifted and talented program. But it's that misunderstanding of what is significance and what it means for something to be significant that kind of leads people down the path sometimes. And so be aware that significance is a high bar. Significance is a high bar. And it's either going to be the bottom 2.5% and the top 2.5%, if you don't care the direction of the difference, or it's going to be the bottom 5% or the top 5% if you do have a question that's more directional. And those are called the difference between two-tailed significance and one-tailed significance. If you want to know if something's better than something else, then you use a one-tailed significance. And so you're only looking at one end of the distribution. If you want to know if something's different from something else, then you use both ends of the distribution. And so it's this, this sort of notion about inference and statistical inference that we get bound up in sometimes, but it's actually, it has just as much error or just as much potential for error in it as any other way of looking at things. And so it is a different logic, a different way of looking at things, but it is the basis of quantitative analysis and the quantitative methodology is to generate scores or generate categories that we then can either test or measure or compare against each other to see if things are related, connected, or to see if things are significantly different. And so we have the two ends of the spectrum. We either want to know whether things are significantly related, which means that they change in certain ways consistent with each other, or are things significantly different, which means that there is a systematic difference, and it's either some cause that we expressed, or at least that's our take on it, or it's some bias that's built into the system based on some other systematic difference. And so that's the nature of quantitative analysis. It's also the nature of quantitative sort of methodology. And there are all kinds of methods, and they all have to do with a particular structure to the research. And so when you build a research methodology, it looks a certain way, and because it looks that way, the data is a certain kind of data, and because of that, you analyze it a certain way. But it all has two underlying assumptions. One, that it's a ratio between what we observe and estimated random error. And two, there's a distribution that's predictable of whatever that ratio is that we look at. Questions? Comments? beyond thoughts that you don't want to share, like, what am I doing here tonight? Okay. You know, whatever. But it is, you know, the thing that you really need to kind of understand about quantitative methodology is, why is quantitative methodology the methodology that we use largely to make decisions about? You know, if we're going to make a big decision about, we're going to adopt something as a technique or as a resource, or we're going to put our money in certain things, or we're going to have this kind of reading program, or we're going to put this other program in place, and we're going to organize a library a certain way as opposed to another way. You know, why do we depend on quantitative analysis to make those decisions? And we do. We absolutely do. Policy decisions are made by, you know, quantitative analysis, typically. And it's because the basic logic of that modern scientific method is built so that you can generalize back to a larger population. So since you randomly draw groups, hopefully randomly draw groups from a larger population, what you know about the groups, by inference, you know about the population. Now, the nature of qualitative inquiry is about depth and understanding, but it's based upon small numbers of subjects who are generally not random. In fact, you pick them for a particular reason. You pick them because they have certain characteristics. You pick them because certain things have happened to them. You observe them because they're in a particular place. Or, you know, there are all kinds of reasons why you collect data qualitatively. And most of it is narrative data or observational data. But the primary reason you collect that data in that manner is so that you can dig deeper on a smaller number of subjects and have an understanding about what's really going on here. But the problem is, that's not random. And so you can't generalize it back to the larger population that they came from. And so that's why we don't make policy decisions based upon qualitative research. Now, I'm a fan of mixed methods research because I think it's important to know what's happening quantitatively and also understand why it's happening. And that works in lots of scenarios to make policy from, but it has a basic quantitative component to it. But almost never will you find policy being made based on qualitative data because it's not random. So you don't know that the information you have is any way representative of the larger population. And so that's why I tell people that are kind of interested in leadership roles, you know, getting into leadership roles, you need to have at least a passing fancy or a passing acquaintance with quantitative methodology. At least understand what significance means, what some of the statistical terms might mean for you, because those are the things that you'll have to make decisions on. And if you don't have that facility or at least a little bit of that skill set, then you'll have to at least bring somebody on board that has that to help you make those decisions, because policy decisions are made using quantitative data, typically. It's all about the numbers for policy decisions. Now, it's also all about the numbers for evaluating policy decisions. So the numbers can get you into a policy, but also the numbers can get you out of a policy if you find out that it's not working the way you thought it would work. But it is, quantitative methodology, quantitative techniques are important for you to have at least a passing acquaintance with, because you have to understand that as you dig deeper into your field, and particularly if you want to get into leadership roles, you're going to have some facility with at least understanding quantitative outcomes. I'll relate one last little story and then I'll let you go. But years ago, when I was first getting into academia, it was really a happenstance. I didn't really plan on being at the university. I just, had gone through a kind of a not such nice divorce, and was, one of those deals where somebody has to leave town. So I figured it was me, because I didn't have a job, and or she had a better job than me. So, and one of the few jobs I could find was an instructor at a university. And I figured, okay, I'll go there. They'll hire me for 2 years, give me a 2-year contract. I'll figure out what I'm going to do then, and I'll go do something else. Well, 30 years later, I left that institution. So it wasn't one of those things that I had planned to do. And I went there had finished my master's degree as an instructor. And so, it required a lot of effort to kind of upgrade, so to speak, to be able to stay there. But it didn't pay very much. In fact, it paid a whole lot less than even instructor roles these days, relatively speaking. And so you did what you could on the side, and I always had I'd started off to be an engineer, and so I had a good facility with statistical sort of stuff and things like that. So I started doing some work with a market research firm as a consulting on the side, away from the university part. And, very quickly got into doing some high-level market research. And, now you go to, say, one of the more famous clients that I work with, if you go to the grocery store, you'll see, you go to the meat counter, you'll find, different meats in the meat counter. And one of those, still a lot of stores carry it. I'm not sure everybody carries it these days. Sara Lee Meats. And, they also do the packaged meats, which they call the pegged meats. But when I was in college and in high school, Sara Lee was a bakery company. They made cakes and breads and, kind of like Little Debbie-like things and all kinds of stuff like that. And they were wonderful. But they decided to diversify, so they were trying to figure out how to get into the meat business. And they were going to buy packing houses in different parts of the country, but they were trying to figure out which meats would sell in different parts of the country. They figured out real early, that it would be different in different parts of the country. What sold in the Northeast would be different from what sold in the South, and what sells in the Midwest and all that. And so, I get a box of surveys or a box of data on paper on a Friday afternoon, and would spend all Friday night and all day Saturday, entering that into a spreadsheet, and then, a couple hours on Sunday, running it on a mainframe that I had access to over the weekend, and putting reports together. And I'd get up at 7 o'clock Monday morning, catch a plane, and be in Cincinnati or Cleveland or whatever, giving a report to the marketing people or the production people at 9 or 10 o'clock the next morning, on Monday morning. And so it all had to be happening between Friday afternoon when I got the box and Monday morning when I got on the plane. And they paid fantastically well. And so it bought first house and all this sort of stuff, and helped me get my kids through college and all that. But at some point, somebody came on board that was trying to equate the amount of effort put in to the outcome. And so they decided, okay, well, we're not going to ship you forms anymore. We're just going to enter the forms ourselves, and we'll just ship you data. We'll just send you a data file, and you analyze it, write the reports up, and that should be worth about half to a third of what we've been paying you before. And I said, no, I don't think so. It's okay. I mean, it's been a nice run, but I really don't want to work for you anymore. That's going to be the deal. And so, I appreciate what you've done for me and what I've been able to do for you. And so, we'll kind of see you later. Because they were trying to equate the fact that it only took me a couple hours to run the data to the amount of time it took actually to prepare the data, which was a whole lot more. And it was a per hour rate they were sort of thinking in their mind. Of course, that's the way accountants think. And so, I said, no, that's fine. I really enjoyed it, but I need to get busier in my academic role and, write some articles and do some things like that. And kind of walked away. 2 months later, I get a call, and, the guy says, okay, well, name your price. And so, I gave him a price, which is basically the same thing they'd been paying me before, because they had figured out that it wasn't the time, it was the expertise and the knowledge. That it's the intellectual property piece that is of value and not the amount of time. And, so that's kind of the thing that I've always, brought to the table with people is that it's not, work is not how busy you are. It's how valuable the work is that you do. And so if you want to be of greater value, you need bigger skill sets. And it's not beyond any of you to add additional skill sets like, understanding some statistical outcomes. You don't have to manipulate it. You don't have to do the stats. You don't have to enter the data. You don't have to do any of that. You just have to understand what the outcomes are. And there's lots of good places to learn that, either on online or local community college or wherever. I mean, but it is a skill set that if you're going to be in a leadership role, you probably ought to pick up somewhere along the way. All right. Well, I'm glad your son likes math, stats in particular, because if I could, I used to go into schools when I was and teach fifth graders statistical concepts. And they understood it perfectly because we didn't use formulas. We didn't do any of this other stuff. We didn't do a lot of math calculations or anything like that. But we did a lot of hands-on stuff with, rulers and, jars full of ping pong balls of different colors, things like that. And it finally got to the point where I couldn't free up enough time to do it as much as the demand was, so I had to kind of step away from that. But in terms of the skill set, the knowledge base, fifth graders can do it, third graders can do it, because youngsters like that are inherently more logical than the adults they live with. I mean, they see things in very logical, straightforward sort of patterns and paths. And we layer all kinds of nuances on everything. And so we have to think about every word and every gesture and every movement. And, those are our hangups, and eventually they'll be their hangups. But, kids are very, very logical and can learn a lot of logical content very easily. All right, I'm sorry, I'm just going on here. Any questions, any comments, any thoughts? I'll open up a couple of other resources on the qualitative side. There's a couple of little pieces down there, but I'll open up some other stuff on the qualitative side. And we'll, as I say, next week we'll talk about qualitative. The next, you should get feedback probably tomorrow, hopefully. Anything, I got to be here all day tomorrow in my little den, and I don't have any big project stuff that I'm working on, so I should be able to read through stuff and get you some feedback. But the next quote unquote draft will be that. It will be looking at the outline that you have for the final project, beginning to fill in as many of the details, as many of the spaces as possible. Taking what you've done for a lit review and beginning, if you haven't already done it, to put it in a narrative form. Taking the elements of the action plan and putting that into a narrative form. And so we're beginning to sort of put a manuscript together now. I'll start looking at APA. I'll start looking at all those things, and this quote unquote manuscript to come in, and that will be on the 21st. So you'll have, let's say I get this out to you tomorrow, I'll give you 2 weeks to put a draft. Doesn't need to be perfect. Doesn't even need to be polished. Just get what you can down in that manuscript format. And then we'll hang on to the other dates. And so the next date after that is in early December. And I'll turn that one around pretty quickly too, because on the 21st, I'll be pretty much sitting at home most of that week too.
Just to double check, you mentioned an outline of the final project. Is that on As You Learn?
Yes.
Okay, is it, let's see.
Well, let me go over there. Let me, it's actually called School Improvement Project Outline. If you'll give me just a second, I'll pop it.
I just found it. It was at the very top.
Yeah, it's in the resource section at the top.
Okay.
Yeah.
Okay.
And, there may be some elements that don't apply to your particular scenario, and I'm thinking in particular, Kelsey, obviously you're doing a kind of a different thing there, and so your drafts will look quite a bit different. She's doing a kind of a part of a pre-thesis sort of prospectus thing, and so that's hers will look a little different. And otherwise, it's pretty much the most everything that you do will be in there. There may be some elements in there or some sections in there that don't really fit with what you're doing. And if that's the case, just kind of, make that comment to me. And if I say, yeah, you're right, there's nothing, you don't need to put anything in there, that's fine.
So for this, we're going to do an introduction and then put our lit reviews and then continue the paper after the lit reviews?
Yes. Okay. There'll be a methodology piece after the lit reviews.
For the research design, Dr. Bolt, will we basically be taking our action plan and writing it out in a narrative?
Yep.
Okay.
Exactly. And this is really kind of as if you were going to actually go into a setting, school, whatever institution, library, and actually implement this intervention and measure its outcomes. You're not actually going to do that, though I think maybe a couple of you are talking about some things that you're already getting into, which is fine. But it's as if you're doing the plan for actually doing this research. Other questions, comments, thoughts?
Question more specific to my situation, but I can just hang around after class.
Okay, that's fine. Yeah. All right, folks, I'm going to stop the recorder and we can